Hi, I'm Olivia, everyone's favorite math teacher. And in this video, we're going to look at something called related rate problems. Related rate problems are similar to what we looked at before. However, they're a little bit different in that instead of being provided with the static values for the functions, we actually have the rates at which things are happening. And those rates are going to be affecting the rates at which the other variables change. So basically, we're looking at situations in which there are non-static situations between the two variables. Whereas before, we had reasonably static situations causing an effective change between the two variables. The example we're going to look at is going to be similar to the spherical cell we looked at, although this time it's a balloon. And it's going to be a little bit of a silly situation. We're looking at blowing up a balloon in order to raise a platform. And so what we're asking is, how fast is that platform going to raise as we inflate this balloon? You can kind of think of it as a silly idea for an elevator. So here's our silly little situation. The air is being pumped into a balloon at a rate of 100 centimeters cubed per second. How fast is the radius increasing when the diameter of the balloon is 50 centimeters? Now, as I said, this is a little bit similar to what we were talking about last time, but this time, instead of asking about how the rate of something is increasing when we're looking at fixed changes, right? When we're looking at here's a radius, here's a volume, what's the rate of change of this when this thing goes from point A to point B? We have simply the rate of change. We don't have a point A and a point B. So we don't know necessarily exactly how we can work with that. We do know, though, how we can relate a volume to a radius. So when we're working with related rate problems, we may not have an immediate ability to work with directly the rate of change of one object and the rate of change of another object. But we might have the ability to work with one variable and the other. However, we do have a tool that will allow us to convert both of those variables into rates of change using that third variable. Okay? And I know that might sound a little bit confusing, but what I mean is you'll notice that we're talking about a rate of change over time, right? And here we're saying how fast is the radius increasing? So fast, that's also time. So we're saying here's a rate of change and we want the rate of change of the radius over time also. So we've got two variables that are linked, but they're changing with relationship to a third variable. And if you remember, we do have a technique that allows us to take something and differentiate it in relation to a different variable. Okay? So our first step here, and I'll explain the process and let you give it a try. Our first step here is going to be to relate not the rate of change of volume to radius, but relate volume to radius. And we know how to do that. We did it in the last video. Then we can relate the rate of change of volume to the rate of change of the radius using implicit differentiation by taking the derivative of the equation with respect to time. And you'll notice that we don't have time in that equation when you write it out. So see what happens when you do that. I'll give you the answer in 3, 2, 1. So, in order to work through this, a good idea is start by identifying the information you're given. This will help you to kind of know where you want to end and also kind of where you're going to be starting. So in this situation, we were given the rate of change of the volume to time. and we were looking for the rate of change of the radius, and we could infer that it was to time because it was saying how fast. So from that, we know that we're given a rate of change for this, we're looking for a rate of change here, and we have a radius here. We know that it's a sphere, so we can relate a volume to a radius, which means through implicit differentiation, we can convert to a volume to time and a radius to time, so we can provide these. And in doing so, we'll also have a radius in our equation. Here we are. Trying to point to the right one. So we get v prime, which is our dv dt, and we get r prime, which is our dr dt. So at that point, we simply need to solve for our r prime and then plug in the values we have. We have v prime, we have r, and then it's just simple algebra to solve and show that at the 50 centimeters, which was a diameter, how we knew that we had 25 centimeter radius. So at the 50 centimeter diameter, we're increasing at a measly 0.0127 centimeters per second. I don't think our ant is going to be having a whole lot of fun. That's not a very fast increase. But this technique, this process, is similar to how you're going to be solving most of these related rate problems. Let's do one more together, and then I'll give one more for you to try on your own. Here's the next one we're going to look at. Now, what I would suggest is when you start this one, start with a diagram. See if you can figure out how to relate the speed of the plane and the distance from the radar station. I'll show you what I came up with in 3, 2, 1. So here's the diagram I came up with. And if you haven't completed your calculation yet, see if that diagram will help you. And here's the calculations in 3, 2, 1. And here were those calculations. Now, I used P for the distance from the vertical point above the radar tower to the plane and R from the plane to the radar tower. So that meant that P prime was that speed they gave us. R would have been that distance I talked about, which they gave us as 2. We needed to calculate that distance P, and there's 2 ways you could have done this. Simple Pythagorean theorem, since we had a right triangle, or if you recognize that that was a special right triangle from trigonometry, we had a 1, 2, square root of 3 right triangle. Got us that would have been the square root of 3. So from that, we simply set up our right triangle situation, do our differentiation, and we get that 2pp prime is equal to 2rr prime. Solve for r prime, the thing we're looking for, and we plug in our values of 500 root 3 over 2 and approximately 433.01 meters per second, or miles per hour. Sorry, getting back into metric there. So let's go ahead and look at one more for you to try on your own. So that was our overview of related rates. I hope that helped you out. And if you have any questions, or if there's one that you're working on and you just need to ask some questions about it, feel free to drop into the comments or join us on Discord. And of course, the answers to the question from earlier will be after the outro.